Okay, take it away.
Yeah, hey everyone. My name's Tom Hilder. I'm a PhD student from Monash University, working with Andy Casey. And today I want to talk to you a little bit about a new technique for analyzing IFU spectroscopy data that we've been developing, and especially applying it to the SDSS-V Local Volume Mapper to resolve faint emission lines. So, what is the Local Volume Mapper? Well, so this is one of the three mappers in SDSS-V, along with the Milky Way mapper and the black hole mapper. And it's a very large optical and near-infrared IFU survey. The instrument itself is located in Las Campanas, Chile. And so I've got this little cartoon on the left because this is supposed to represent the actual integral field unit itself on the local volume mapper, which consists of like a bunch of fiber optic cables next to each other in this hexagonal pattern. And in each one of these, you get a spectrum of the sky. And so I'll probably interchangeably call these either spaxels or fibers throughout the talk. And actually, the size of the whole IFU is this, and it has 1,801 fibers. And in terms of the size on the sky, it's about half a degree across, which conveniently for talks is about the size of the moon. So every single pointing of the telescope, you're mapping a part of the sky, basically the size of the moon. And so this puts LVM in this like new regime of like ultra wide field spectroscopy. But in terms of the spectral coverage, as I said, it's like optical and near infrared, and then the spectral resolution is mostly on the order of about 4,000. It varies a little bit. And then, yeah, what are we pointing it at? Well, like the whole Milky Way. So this is a map of the southern sky. The little white hexagons are regions that have already been observed by LVM, and the red hexagons are regions that plan to be observed. And so I don't know how well it's coming up on that, to be honest, but some highlights. So we have the Milky Way, where we've got sort of like resolution of less than a parsec per spaxel. The Large Magellanic Cloud, where it's more like 10 parsecs per spaxel, and Orion, which is less than a tenth of a parsec per spaxel. And then we've also got like the SMC, GUM Nebula, and then there's these like sparse all-sky pointings as well. Okay, well, besides the fact that it's really cool, why are we doing that? And sort of the rough idea is to try and understand both the small scale effects and large scale effects of stellar feedback on galaxy evolution simultaneously. So we've got this kind of like diagram where you've got H2 region that's like resolved at different scales. We've got like low resolution, high resolution, and most extragalactic surveys are sort of on this like left-hand side of the plot where very low resolution. And LVM's targeting the right-hand side of the plot, but locally in the Milky Way and the Magellanic Clouds. And the point is that you can resolve individual sources of feedback and individual shock fronts. And so you can sort of do this like small scale and large scale evolution picture at the same time. And a key like data product, I guess, for the local volume mapper is emission lines. And these allow you to map like the density and the temperature and the pressure and the kinematics of nebulae and gas in the ISM, in the ionized ISM specifically. And of specific importance is weak lines. So these lines called like auroral and recombination lines are really interesting for a lot of like important science questions. And so I'm going to zoom in on one of them, which is the abundance discrepancy problem, which is basically this like long-standing disagreement between methods trying to determine ionic abundances in H2 regions. When you do it with like methods that use strong lines and methods that use really weak lines, you come up with this systematic disagreement. And so like LVM is hoping to answer, why does that happen? So, these pointings of the telescope are sort of next to each other on the sky, and they create this like tile pattern. And literally we call these like tiles in LVM. So if we were to zoom in on just one of these, I'd like to highlight that kind of the state of the art in IFU spectroscopy is that you model each of the spectra in each of these fibers individually. They like don't know anything about each other. But zooming back out, they're literally right next to each other on the sky. And so if this is pointing at a nebula or something, the spectra that are right next to each other are going to be more similar than the spectra that are far apart. And so actually, it would be nice to account for this in some sort of model where you like leverage these spatial correlations that are really in the data in order to get down like really as far into like the like highest precision thing that you possibly can. And so that's where my project comes in. So broadly, we're calling these like spectrospatial models. And the concept is actually like really simple. So up in the top right, I've got one pointing of LVM, and I've picked some random fibers to plot the lines. This is H alpha. And you can see, looks like a Gaussian, so maybe you'd want to model this as a Gaussian. You've got like a bit for your emission line, a bit for your continuum, and you're going to be fitting for the flux in each like fiber, right? And so the idea is just instead of having a number that I determine for each fiber independently, I have a non-parametric function that's a function of the position on the sky, and instead I want to infer that function, and with all of the data all at once. And so in this case, that function's giving you the flux, but in general, you can do this for any like quantity that would be in your spectrum model. So like you could do the redshift, or the line widths could be continuous on the sky as well. And in the results I'm showing, that's what we've done. But I haven't told you how we're going to do this yet. So this is where Gaussian processes come in. So for the uninitiated, the rough idea with the Gaussian process is you have some like unknown function, and if I simulate some noise draws from this function, and then I like take with measurement uncertainties, and then I forget the function, I want to like recover that function in some sort of like infer the function from the data, right? And so with a Gaussian process, you basically put a distribution over the space of possible functions. And the way that you do this is by specifying the covariant structure of the functions that you allow. So if we pick like this covariance kernel, which is called the radial basis function kernel commonly, you get functions that look like this. If I pick some other kernel, like this is the exponential kernel, then you get these jaggedy things. Or if I pick this kernel, which is Matern 3/2 kernel, you get sort of like some compromise between those two. And so the nice thing is that now, I've made up some functions, but I can condition this distribution on the data, like one point at a time, in order to refine the like space of functions that are allowed, having observed the data. And then, since this is a distribution, I can get a prediction of the mean function, and that mean is the thing that we'll want to use in this analysis. And then, you can compare it to the original thing. And so that sounds really good, but if you know anything about Gaussian processes, you know that this scales like terribly with number of data points. Naively, a Gaussian process is like order n cubed, and we've got like tens of thousands or hundreds of thousands of spectra that we want to use all at once. And so there's this really nice result from applied math that I want to go through briefly, where you can represent a Gaussian process with a Fourier transformation. So here I've got like a sum of sines and cosines, and I'm basically going to like include one at a time in my fit and watch as it refines as I include more and more functions. And you can see that this starts to approach, fitting the data more and more. But as I get up to having the same number of data points and modes, my function just goes exactly through the middle of all of my points, which is like useless and not what I want. Like that's not the GP. The GP is the light thing. So I'm going to do something crazy. I'm just going to keep adding modes, and actually it's just going to get even worse. So this will approach 0 everywhere, except it'll have like Dirac spikes at all of the points eventually. But if I weight this using the Fourier transformation of the kernel function that I want, actually it's indistinguishable from a Gaussian process. And so that also sounds good, but doesn't work, because this sum that you have to do is order n cubed, and you can't use an FFT for this because the points are not on a square grid. But there's this other result from applied maths called the Flatiron Institute non-uniform fast Fourier transform that lets you do this in n log n time. And we wrap this in JAX to allow for like auto diff and other stuff. I'm going to go a bit quicker. So here's some results from doing this for the Rosette Nebula. This is H alpha, which is like the brightest line. So it's like the easiest thing, and you'd hope that it works, and it does work. And I'm not sure how all these maps are showing on the projector, but we don't have any sort of like artifacts from individual pointings. You can see sort of where you'd think they would be by the edges, and all of these maps are like smooth across the sky. And then, I promised you faint lines. So here's helium-1, which is a weak recombination line. It's like at least 100 times weaker than H alpha. And you see that we resolve the structure of the nebula really well, much better than like a perspaxal approach. The LVM DAP doesn't even do this line in a perspaxal approach. And if we look at the individual fibers and compare the model to the data, you can see just how noisy the individual spectra are. So in the future, we're sort of hoping to apply this to like a lot of H2 regions in LVM to get these like faint line emission maps that you can't with other methods. This method also applies for a very natural way to combine dithered observations, because you can just put them all into the model and fit them all at once. And in the Magellanic Clouds, we have this like 7-point dither pattern in LVM, so I think that's very promising. And then we have this other idea that you could like couple a strong line and a weak line if their ionization temperature is very similar. I have some like toy models with some good results in that if anyone's interested. But the idea is that you can do really low signal to noise stuff if you have that. And then beyond LVM, I mean, I think this is applicable to basically any IFU spectroscopy setup for like extragalactic surveys or basically anything. And yeah, this is a false color image I made using 3 lines in Rosette, and I'll just leave this up and take any questions.
Okay. Okay, thank you very much. Do we have some questions in the audience? Okay, I'll ask one. There was a term, was it dithering or
Yeah.
What does that mean?
It's just like, well, a dither is like a pointing of the telescope. So they just point like at basically the same place on the sky, and they move it around a little bit in this like pattern. So the fibers sort of like cross over with each other in the end. And so you can combine those in lots of different ways and hopefully get higher spatial resolution without actually having a higher spatial resolution. Yeah.
From the audience, we got one back. I'm not sure who was up first, but
yeah,
just back at the back,
yeah,
and then back over there, and then on the side.
Cool. Thanks, Thomas. Super nice idea. I was wondering about how far away, right? To which distance can you still correlate these different spectrals? Like, have you checked for helium or for other ones? Like, how much are they still correlated over like arc seconds or even further? Thanks.
Yeah. So I mean, in practice, what we're doing is picking a covariance function, and then we're optimizing for the like correlation length, I guess, in it. So most of the time it ends up being like quite local and small. I think that I've tried some really low signal to noise stuff, and in that case it tends to prefer like quite a long length scale, because I think that it's like that's kind of the best case. The best thing you can do is like a low spatial resolution. So you're kind of like integrating a lot of information. Hopefully that answers your question.
Really quick question. What was the name of the package that you used for this?
We made it. There's no package.
Wasn't there flat iron something?
Oh, sure. Yeah, the FinUft. Yeah, but that's just a package for doing non-uniform FFTs. So, yeah. Yeah.
Another quick one from me. Really nice to see this applied mathematics trickle on through to this application. What was the computational requirements for this compared to like a typical per-spectral approach?
Oh, sure. So my understanding is that the LVM DAP takes like a few hours to a day to run on a server. I mean, I'm not doing all of the lines like they are, but each of these takes me like a few seconds on my laptop at the moment.
So it's faster, not slower.
Yeah, it's very fast. Yeah.
All right. Is there one final question at all? In the middle again. Yep. And can the next speaker just come up, please, and get ready? Thank you.
With this approach, can you like combine different surveys into like one big like high resolution spectrum?
There's no reason you couldn't in principle. I mean, you'd want to understand and model some of the like I guess the instrumental differences between the surveys and other like systematics that would be different between the survey. But yeah, you could like if you have the model predicting like the fluxes, and then you can like have some way that those fluxes predict this survey and predict this survey, you could fit it all at once. Yeah.